Hey, it's Sam. This year I'm going to be doing USACO, United States of America Computing Olympiad. It's a sort of coding competition. There are 4 competitions per year. This being my first year doing it, I'm just kind of introducing myself. There are 4 levels. There's bronze, silver, gold, and platinum. You start off at bronze, so I've just been practicing some bronze problems to practice my skills. And I've only done 3, but I came across this problem, the lost cow problem from 2017. And I have a somewhat interesting solution, I think, that I would like to go over. So here we are, USACO 2017 US Open Contest Bronze. Problem 1, the lost cow. Farmer John has lost his prize cow, Bessie, and he needs to find her. Fortunately, there is only one long path running across the farm, and Farmer John knows that Bessie has to be at some location on this path. If we think of the path as a number line, then Farmer John is currently at position X and Bessie is currently at position Y, unknown to Farmer John. If Farmer John only knew where Bessie was located, he could walk directly to her, traveling a distance of absolute value of X minus Y. Unfortunately, it is dark outside and Farmer John can't see anything. The only way he can find Bessie is to walk back and forth until he eventually reaches her position. Trying to figure out the best strategy for walking back and forth in his search, Farmer John consults the computer science research literature and is somewhat amused to find that this exact problem has not only been studied by computer scientists in the past, but that it is actually called the lost cow problem. This is actually true. The recommended solution for Farmer John is to find Bessie is to move to position X plus 1 and then reverse direction and move to position X minus 2 and then go to position X plus 4 and so on in a zigzag pattern, each step moving twice as far from his initial starting position as before. As he read during his study of the algorithms for solving the lost cow problem, this approach guarantees that he will at worst travel 9 times the direct distance, absolute value X minus Y, between himself and Bessie before he finds her. This is also true, and the factor of 9 is actually the smallest such a worst-case guarantee any strategy can achieve. Farmer John is curious to verify this result. Given X and Y, please compute the total distance he will travel according to the zigzag search strategy until he finds Bessie. So, there's the problem. It inputs positions of X and Y as range between 0 and 1000, and you're just supposed to output your program is just supposed to output how far Farmer John is going to travel. So in tackling this problem, there's a sort of obvious solution, which I've heard happens a lot with bronze problems, and the other 2 bronze problems I've done also, what they did is they used simulations. And you can use a simulation for this problem too, right? You can simulate Farmer John going from point 0 or from point X to X plus 1 and then to X minus 2 and then to X plus 4 until Farmer John finds the cow. So a simulation is a kind of an obvious solution, but I thought, sometimes simulations can be inefficient and sometimes a more elegant mathematical solution can be more efficient. And I made what I would think is a somewhat elegant solution, but unfortunately it's not any more efficient, I think, in terms of time complexity than a simulation, but I didn't realize that at the time. Anyway, I think it's still a pretty interesting solution, so I'm going to go into it. So what I did to start off my solution is I used a number line. So here I am with my number line that goes from -4 to 4, and what I started off by doing is just writing how much Farmer John would need to move every step of the way in finding his cow. So first he would go from 0 to 1, plus 1, and then he would go from 1 to -2, plus 3, and I'm just gonna... So what I have now here is how much Farmer John would move, during every step to get to this number on the left. So each row, has its own little thing going. And these numbers on the right would be when Farmer John is moving to the right, and these numbers on the left would be when Farmer John is moving to the left. So even though they're plus, that's just contributing to how much Farmer John is moving, not the direction he's moving. So I was looking at these numbers, and I was trying to find, something I could figure out, some mathematical thing I could figure out. Like we got plus 1, plus 3, plus 6, plus 12, plus 24, plus 48, plus 96. And you'll notice that starting on +3, it just keeps on doubling. But from +1 to +3, it just doesn't double. So I was scratching my head about why does it go from no double to double? And seeing as, there is some sort of binary component, right? It keeps multiplying after, or once we hit this +3, I decided to just write some binary and see if there were any patterns I could notice. So if we start at +1, right? What is 1 in binary? 1 in binary is 1. We move on to +3. What is 3 in binary? 3 is 1, 1. And then I was like, okay, that's interesting. We get 1, then 1, 1. And I for a second thought, hey, maybe we'll get 1, 1, 1 for the next one. Unfortunately, or maybe fortunately, I don't know. That didn't end up being the case, because what 6 is, it's 1, 1, 0. So I was a little disappointed that we had gotten a 0 there, kind of had broken that pattern, but I went on nonetheless. Let's see what happens when we go to 12, and then found, oh wow, 12 is 1, 1, 0, 0. How interesting. And I decided to keep going. We have 24, 1, 1, 0, 0, 0. Even more interesting. 48, 1, 1, 0, 0, 0, 0. And then I went up to 64, 1, 1, 0, 0, 0, 0, 0. Hold on, look at this. We have 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. And except for the first one, because the first one only has 1 digit. So I'm noticing we get 2 1s for the first 2 digits. And then everything else a 0. And I was like, wow. And this right here is the basis of my solution, because now I know that every time Farmer John moves, the amount he has moved, right, his total movement is going to increment by, what is it? It's 2 to the n plus 2 to the n minus 1. Every time Farmer John moves, his movement is going to increment by this. That is the basis of my solution. And, n is going to increase, and all I really need to do is find out until what point will n increase. So since this is this is increasing, powers of 2 here, because it doubles every time he moves. I thought maybe I can use some sort of base 2 log system to figure this out. Log base 2 of the difference between Farmer John and the cows, and the cow. And that was pretty close, but this idea takes some refinement, because we have to note that Farmer John is going back and forth, back and forth, back and forth. So say we started with the cow at 1 and Farmer John at 0. So this would be, what is the difference between these is 1, and what is log base 2 of 1? Well, log base 2 of 1 is 0. And then say, and then over here, right, cow is at minus 2. This would be 2, a distance of 2 away from Farmer John. I know it's negative, but we'll talk about that later. That's going to be, log base 2 of that is going to be 1. So what I realized is every time the log base 2 of it is odd, the cow is going to be on the left side. And every time the log base 2 of it is even, it's going to be on the right side. So that's interesting. Now, what if, this shouldn't be a -4, that should be a +4. Now, what if the cow is not at a perfect power of 2? What if it's at 3? I decided that the best way to go about this would be to go to the next power that appears on the right-hand side. So the next even power, right? Because we have the odd powers on the left side and the even powers on the right side. 2 to the power of 0, 2 to the power of 1, 2 to the power of 2. So this would be the highest, if we had to round up the log base 2 of this, the next even power would be this one. And same thing if we're on the left side. If on the left side we have a cow at -1, well then not really rounding out, it's more like rounding down the situation. Then we get to the closest odd power, which is at -2. So this is how we figure out how many incrementations we have, right? How many of this we have. And then if it's not a perfect power, then all we have to do is, once we have our total, we subtract this distance. So if we're at 3, we're going to go through adding this on and on and on. And then at the end, we're just going to subtract 1, because that's the difference between our closest even power. So now that I've gone over the basis of the solution, I'm going to show you the code. So here we are over at the code. I wrote it in C++. We start off by getting the farmer position and the cow position from user input. Where the stuff really starts is the difference. We're finding the difference between the cow position and the farmer position. So this right here, if cow position is greater than farmer position, we're going to get a positive number. And if cow position is less than farmer position, we're going to get a negative number. And we don't want to take the absolute value of this, because if the difference is positive or negative is crucial to figuring out how much Farmer John needed to travel. So right here is the log part, right? This is where we find out how many times Farmer John needs to turn around, essentially. So this is the log base 2 of the absolute value of the difference. We are using the absolute value here, and we take the seal of that. We're rounding it up, because remember, if it's not a perfect power, the strategy I took is to go for the closest higher power and then just subtract the slight difference at the end, because that's going to be the entire difference. Now, here's another important thing. If we have an odd log, right? If we have an odd log and the difference is positive, then we're going to need to bump it up another log, because the correct log for that number is actually on the negative side, and that's not right. And then the same thing for the negative side. If we have a negative difference but we have an even log, then that means our log is on the wrong side, so we need to bump it up another one to get to this cow's position. So if either of those conditions are true, then we just bump up our log by 1. Now this part, I don't know how necessary this is. It's unclear to me if they want you to account for this, but what if Farmer John runs out of room on one side of the path or another? That's all this handles. I'm not going to go into too much detail about that. Now this is the most interesting part, right? So what this is a loop that iterates however many times our log is. And what we need to do is we need to, every time it goes through, we add the path of the path distance. We add to it 2n plus 2n minus 1. So I think I found a kind of clever way of doing this. We have 2 increase variables. So this increase variable is 2 to the power of n, which in this case is I, right? Because n increases as we as we go through the log 2. So there's that. And then this is just accounting for if we don't have enough room in the path. And then we add that to the path distance. And on top of that, we add the previous increase, right? The previous increase would be 2 to the n minus 1. Now, we should remember that for the first one, plus 1 in binary is only 1. It's not 1, 1, because there's only one digit. So the first time the previous increase is going to be 0. But then after that, we set the previous increase to the current increase. And then when we loop around again, the current increase will have changed. So that's how I did that. And then right here, final step. Remember, if we need to round up the power, then now we need to account for that in the end. So what we do is we find the distance of our quote-unquote ending point, right? Power 2 of log. And we can't just use log 2 of the absolute value of the difference, because remember, that log might be on the wrong side, those even and odd logs. So we do need to use our original log number. And then from that, we just subtract the absolute value of our difference. And that'll get us the difference between our, 2 to the power of our log and where the cow actually is. And then we just subtract that number, and we get the answer, and we see out that. So I'm just going to quickly demonstrate that in action. 2 input numbers, 3 and 6. And the correct answer, I believe, should be 9. So here we go. There we go. Gives me 9. Thanks for watching. If you found the solution interesting, then let me know. I'll see you in the next video.